Hi, Physics 2. Mr. Janowski here. So this is the second part of the chapter 15 and 16 slides, and I am really going to try to make this one short. I keep failing at doing that, but I'm going to try to make this one short. Do now to review. What symbol do we use for the speed of light, and what is the speed of light in meters per second? We always use lowercase letter c to be the speed of light. We don't use lowercase c for anything else, and it's 3 times 10 to the 8th meters per second, or 300 million meters per second. So that's pretty fast. How fast is that in miles per hour? You might remember from Physics 1, we have a way of converting from meters per second to miles per hour. That's the bloody cheetah. So just take the number and double it. So yeah, the speed of light is about 600 million miles per hour. So very, very fast. So what is the first postulate of special relativity? That is the equivalence of physical laws. So the laws of physics are the same in all inertial frames of reference. And what is the second postulate of special relativity? This is the constancy of the speed of light. This says that the speed of light in a vacuum is the same for all inertial frames of reference, regardless of the motion of the source or the receiver. So if you remember back to the question from last time with throwing baseballs in the back of a truck that's moving down the road versus shining a flashlight from the back of a truck that's moving down the road at some large proportion of the speed of light, you have to add up the things differently, and you end up with different answers. And the way you add them up, it doesn't seem to agree. It's very weird. And that's all due to this, the second postulate. So yeah, events in proper time, delta t naught. So because of this weirdness and the weirdness that's going to come up with time and also space, we need to be very, very precise and define things like events very specifically, which is going to seem a little weird, but that's how you do it. So an event is a physical occurrence that happens at a specified location at a specified time. So a photon leaving the bottom mirror of a light clock is an event. A photon arriving at the top mirror of a light clock is also an event. So proper time, delta t naught, that's how you say it. That little O, more on this in a second, it's not a letter O, it's a zero, or naught, is the amount of time. Proper time is the amount of time separating two events that occur at the same location. So if we're both looking at my light clock as I fly by, I'm going to be present at both of the events. Therefore, I will have proper time. You will not be present at both events. You might be present at the first event. If my photon leaves the bottom mirror at exactly the moment that I'm passing you, you were there at the first event, but by the time my photon gets to the top mirror, you're not there anymore. I'm still there. So, yep, what's written here is what I just explained. So yeah, I have proper time because I am present at both events. You are not present at both events. Whether you're present at only one or you're present at zero of the events, you're going to measure what's called observed time, delta t. And then a note about what's going on here. Again, the O, this is a zero. It's not a letter O. And this is just going to be confusing. I'm trying to head off this, this little problem area right here. It's a zero, not a letter O. So this is not O for observed. This is zero for not. So delta t is observed time. Delta t naught is proper time. Yeah, it's weird. And so here's our formula for time dilation. And we're going to see that lots and lots of relativity equations are going to have this term in there somewhere. Square root of 1 minus v squared over c squared. So let's work through a couple of problems real quick. So I'm going to fly by in a spaceship traveling at 86.6% the speed of light. So you could write my velocity has v equals 0.866 c. So according to you, how long does it take for my clock to tick off 1 second? So what are the two events we're talking about? Let's get a clear idea of what these events are so we know who has proper time and who has observed time. So the two events for my clock to tick off 1 second are a photon leaves the bottom mirror of my clock and a photon reaches the top mirror of my clock. So who's present at both events? You or me? I am present at both events. Therefore, I have proper time. And a quick word on this, it's called proper time. That doesn't mean that my measurement of this is any more accurate than your measurement. I know proper seems to imply that mine's the right one and therefore yours must be the wrong one. Again, they're both actually going to be right. as long as you specify the frame of reference. It's weird. So yes, a strategy for when we're doing these special relativity problems. So yeah, you're going to see this ugly term a lot. So my suggestion to you is when you see this term, as soon as you can, take it over to the side of the page. So you're starting the problem, you're working on the left-hand side of the page. When you can, just take this term over to the side and do all of the algebra very carefully and very deliberately and turn this ugly mess of nonsense into just a number. So you would do this you should do this in any problem where you know V going in. So some of the problems you'll know V going in other problems you'll know the other things and you have to solve for V. But if you know V going in, take this piece of algebra over to the side, do it all separately, do every step carefully, and turn that mess of nonsense into a number. So back to the problem we're doing. So yeah, I fly by in the spaceship at that speed. How much time does it take for my clock to tick off 1 second according to you? So here's the time dilation formula. We had just solved for all that mess of stuff. So we turned this ugliness into a number, 0.500. So now we're going to plug in the numbers. So I have proper time because I'm there at both events, and proper time is 1 second. So this ends up just being 1 second divided by 0.50. 0.500. So 1 second divided by a half, which is the same thing as multiplying by 2. So 2 seconds. So what this means is you're going to experience 2 seconds for every second that I experience from your point of view. You're going to watch my clock, and if you're timing my clock tick off 1 second, you're going to say that it takes 2 seconds to do that. Because my moving clock to you looks like it's running slowly. So we're going to disagree about time. So this is a very real effect, and it's very weird. It's about to get weirder in the next problem. So different situation. When we're doing relativity problems, we love talking about twins because talking about twins really highlights some of the weirdness going on. So let's imagine that Alice and Denise are actually twins. I never told you that last year, but yeah, they're twins. So they're both 17.0 years old, which is a weird way to state your own age, but yeah, they're 17.0 years old at a certain point. So they're here on Earth. What's going to happen is Alice is going to get on a rocket ship and she's going to fly away to the star Vega, which is about 25 light years away. She's going to travel very, very fast, and she's going to leave her twin sister behind. So we'll start by looking at just the one-way trip, Alice flying to Vega. So Denise is standing there on Earth, and she's going to watch how long it takes Alice to do this trip, and Denise is going to say that it takes Alice 25.25 years for Alice to make this trip. Alice, on the other hand, is going to say, no, that trip only took 3.56 years. So something very weird has happened. I'll go over the weirdness. We'll do the math, then we'll go over the weirdness. So our question is, how fast did Alice travel? So step, what are we looking for? We're trying to solve for velocity. So what we're going to do is take our time dilation formula, and we're going to do some algebra, and we're going to solve for v. So this is the other type of problem. In the first type of problem, we knew v at the beginning, and so we could solve the algebraic ugliness and turn it into a number. In this problem, we know all of the other things, and we're trying to solve for v. So yeah, you start with the time dilation formula, do some algebra. So multiply both sides by the ugliness. That takes the ugliness from the bottom on the right, puts it on the top on the left. Divide both sides by delta t, observed time, which takes it away from the left completely and puts it on the bottom on the right. At this stage, we know these numbers. We know what proper time is, and we know what observed time is. So pro tip of the day, when you can do this, sub in the numbers and turn this ugliness into just a number, and then ask your calculator, what's 3.56 years divided by 25.25 years, and you'll end up just with a number, 0.140990. So yeah, I'm pointing this out because last year I always said, no, keep it in letters for as long as you can and just throw all of your numbers in at the end. That's usually very good advice. But when you're doing these relativity problems, and you'll figure this out as you go along, when to do this and when not to do this. But frequently in relativity problems, it's going to make the most sense to throw in the numbers a little bit earlier and turn some mess of ugliness into numbers and then turn this slightly uglier set of numbers into just a single number. And this will make things go easier. So yeah, you do it. We turn it into here. And then you just have to do the algebra very, very deliberately from here on out. So you do all that, do all the stuff. I'm trying to keep the video short. I'm not going to describe the steps in detail. I will make a couple of tutorial videos after this where I'm showing you how to do these things in more detail. But for now, I'm trying to keep the slides video short. So you do all this, and you end up with v is equal to 0.990c, which is to say the velocity was 99.0% the speed of light. So that's how you do the math. Now let's not lose the plot. Let's look at what actually happened here, because what happened here is really, really weird. But this is what happens in special relativity. We started out with Alice and Denise being twins on Earth. They're both 17 years old. Alice goes on a one-way trip to a distant star, and according to Alice, that takes about 3.5 years. So according to Alice, when Alice, arrives at Vega, she went from being 17 years old to being about 20 and a half years old. And she's right about that. She is 20 and a half years old when she arrives on Vega. Denise, meanwhile, is watching this whole time, and she says, well, it actually took 25 and a quarter years for that to happen. So Denise, standing on Earth, ignoring the look back time and the fact that Vega is 25 light years away, when Alice arrives on Earth, Denise won't be 3.5 years older. She'll be 25 and a quarter years older. So, yeah, Alice is now 20 and a half years old. Denise, meanwhile, is now 42 and a quarter years old. So our twins are no longer the same age as each other. Very weird. And just to, emphasize this weirdness, let's say Alice now decides, okay, I've had enough of Vega. She flies back right away at 99% the speed of light. When she gets back to Earth, how old are these two people? According to Alice, she herself aged 3.5 years on the trip out there. So she got to be 20 and a half years old, and she aged 3.5 years on the trip back. So she's now about 24 years old. Denise, meanwhile, said that each leg of Alice's trip took about 25 years, which means when Alice comes back, and Alice, again, now being 24 years old, Alice's twin sister Denise is going to be 17 plus 25 plus 25. Denise will be 67 years old. So that's crazy. It's entirely true. I mean, we've never done this, obviously. We don't have the rockets for this yet. But yeah, this is what relativity tells us. And relativity works. This is true. This is what would happen. So you would have, you started with two 17-year-old twins. And at the end of this problem, you have one of those twins being 24 years old and one of those twins being 67 years old. Very weird stuff. So to review quickly, what is the difference between special and general relativity? Special relativity only applies to the special case of inertial frames of reference. General relativity applies to all frames of reference, inertial and non-inertial. So general relativity is the bigger formula, is the bigger theory because it includes everything. And general relativity also includes gravity. So what are the two postulates of special relativity? The first one is the equivalence of physical laws. The second one is the constancy of the speed of light. And what is our formula for time dilation? Our formula is delta t, which is observed time, is equal to delta t naught, proper time, divided by this ugly term that we're going to keep seeing, the square root of 1 minus v squared over c squared. So in the slides, there's also this link, or you can just, go to YouTube and search for it. It's a TED Ed video, Einstein's Miracle Year, that covers all the things we talked about in the first part of the slides, and what an incredible year 1905 was for Albert Einstein. At the time, amateur physicist and professional patent examiner. That's it. As I said, I'm going to make a couple of separate videos about actually doing those problems in a little greater depth. But for now, this is the slide video, and I don't see the running clock. I have no idea how long this took. Hopefully, it was shorter than the other ones. Hopefully, that helped.